Okay, next we are going to work on example number 25 on page 261. The example is about a box with an initial velocity of 5 meters per second, and it is allowed to slide horizontally across the surface. The coefficients of friction between the box and ground are mu k 0.2 and mu s 0.5. Determine the velocity of the box after it has moved 1 meters, and the distance the box will slide before reaching a stop. Just be careful because you cannot assume after 1 meters the object will stop. Okay, so we will find what is the speed after 1 meters and how far it traveled before stopping from initial case. One thing to keep in mind, we are going to use this equation because we have friction. That's kind of the definition, so you can even put like three lines instead of just saying equal, but it is defined as that. And if we go to now the layout, assumptions, yes, one-dimensional motion and there's no drag force. You can add more stuff if you like, but we do talk about some of the things in the equation, energy conservation equation. And the plan is, again, we are using energy conservation, and if needed, we will add other stuff. We will revise our solution depending on how many unknowns we have. Estimations, so since it's gonna eventually come to a stop, I would definitely say at least like the velocity after 1 meter should be less than 5 meters per second. I think that's a good estimation. You can say a few meters per second if you like. And the distance wise, since the coefficient of frictions are not too high, and it's in motion, so we're going to use the mu k instead of mu s, which is mu k is very small. I don't think at 1 meters it's going to lower its speed much. So in order to reach to zero velocity, I think it's going to take more than a few meters. So here it's shown as 10 meters. I think order of magnitude, I would also choose 10 instead of 1. Okay, and the solution, we start with the energy conservation equation, or you can also start with the energy free body diagram. To show when we show the free body diagram, we have normal force upward, weight force downward, and the kinetic friction to the left. So hopefully it's clear why we are using kinetic friction, because it is in motion, right? We also showed our x and y axes. Next, we work on the energy conservation equation, now we have to split it in more detail, so it's a little bit more specific now. Potential is split into two forms, and also the change in internal energy is split in two forms. As usual, we are going to simplify first. So if you scan through them, there is a change in kinetic energy because velocity or speed is changing. But it is horizontal, so there's no elevation change, so I'm getting rid of delta UG. There are no spring-like objects, so I'm getting rid of change in elastic potential energy. There is no temperature or pressure changes related to anything but friction. Okay, so that's why delta I goes to 0 as well. But delta IF this one is due to friction, so the temperature change due to friction, for example. So we are going to keep that. And again, chapter 8, mostly the energy term, so I'm going to ignore the work term of the coming from the friction. And we are going to think about this work later on, as we usually do. In heat transfer, there's no extra heat added or taken away from the system, so we are going to ignore that as well. So what we have then is delta K plus delta IF equals to total work done. And once again, that work term is due to all forces except weight force, kinetic friction force, and the spring force, because we already thought about their energy form. And so then we're going to think about this work term a little bit more. Since we are ignoring the weight force and the kinetic friction and we don't have any spring force, the normal force is the only one from our free body diagram, so we are checking that. But the normal force is perpendicular to the displacement because displacement is to the right along the x direction. That means it doesn't do any work. So that will mean there is no work done. okay, to put in the energy conservation equation. Then we simplify it more and then expand the equation. It becomes delta K is final minus initial. And again, this is the definition of the delta IF. It is positive, not negative, positive FKD. So we are using this definition here. And work done by friction was negative FKD, so remember that, okay? Work done by friction is negative FKD, but since the change in internal energy due to friction is on the left side, when you put it there, it became positive. Again, that's the definition. So that's what we used. Again, that is given in the equation sheet. And next is going to be, so we are keeping both of the kinetic terms, although in one of the parts, we are going to say final velocity is 0, but now we have the equation in general. Now this is the time that we can apply it for both parts, and you don't need to do it twice. Okay, if you have applied, like put the numbers in earlier, you needed to go over from the beginning and apply the energy conservation and everything. It would take much more time. Okay, so but when you look at this equation, let me get rid of a couple of things here. So we are focusing on this equation now for both parts. What we see is for the first part, we have Fk is unknown and also V final is unknown. And we're trying to find V final, but we don't know what the kinetic friction is. And for part B, we're finding the displacement, and V final is going to be 0, but Fk is also unknown. So there are two unknowns for each part, and we only have one equation so far. That means we are revising our plan. Energy conservation wasn't enough. We have to get help from something else, and that will be the Newton's second law, because we are looking for the force, right? We want to find out what Fk is. So the Fk equation, I'm gonna write it here, mu k times n. That means we need to figure out what normal force is. Since normal force is along y direction, we are going to start with Newton's second law along the y direction, and this acceleration is 0 because the object is not moving or accelerating along y direction. And we have normal force upward and weight force downward, so weight is positive because we chose upward to be positive. That gives us normal force equals to weight force, so that detail should be shown. And what we're going to do next is we are going to put that information in the friction equation. So when you do that, in this line here, we get mu kn becomes mu kw, which is weight force, and weight force is mg, so we are replacing that with mg. Now we're ready to put this into the energy conservation. Again, this term was this was the term which had FKD. So FK has been changed with that, but since we put the term on the right side, it's also negative now. One thing we see is all the masses cancel out. What does that mean? It means that any object, okay, regardless of its mass, which is set to move at 5 meters per second across the frictional floor, will slide the same distance, provided they have the same mu k. Okay, maybe that's not very intuitive, but this is what the equation tells us. Okay, so now for part A, since we simplified our equation, we're just going to say, okay, I have initial velocity to be 5 meters per second, and d is given as 1 meters, and I have some other stuff known as well. And what is the V final? We are just plugging numbers in, solving for V final, which is less than 5 meters per second, and that's as we expected. But it's not much less. If you see, it's like a little bit less than 5, but not too much. And again, this is due to very low mu k friction coefficient. Okay, 1 meter wasn't long enough to reduce the speed much. And for part B, where we find the distance at 0 velocity final, so that first term is going to go away in this case. Plugging the numbers in again, solving for d, that gives us 6.38 meters, which is much more than 1 meters. as expected. And again, we focused on the energy conservation, but we also needed to use the Newton's law as well to figure out what the normal force is, so that we could use the definition of friction, okay, in the energy conservation. Hopefully, how we manipulate the energy conservation with the friction case is clear. Again, you have two ways: either keep delta IF or keep work done by FK. Do not keep both of them. You have to choose one of them, and we will mostly choose the energy form from now on.